In this section, we will learn how to compare two data sets where the data values in one set are naturally linked to data values in the other set. When data values are matched or linked, the data sets are not truly independent, and we have what is commonly referred to as paired data. In paired data studies, subjects or objects have been matched on some important characteristic. The advantage to pairing is that the inter-subject variability has been reduced, making it easier to uncover significant differences. As our first example, let's consider a situation where employees switch from a 5-day work week to a 4-day work week. We are curious if this results in employees driving fewer miles annually, since now they have to travel to work one less day. The table lists the name of the employee as well as the annual miles driven on both work schedules. Here the natural pairing between the two data sets is that the numbers in the 5-day column correspond to the numbers in the 4-day column because they were taken on the same employee. There is a reason to match 2,798 with 2,914 because both observations belong to Jeff. If we failed to recognize the pairing here, we might incorrectly run this as a two-independent sample test. This would result in a p-value of 0.4, and we would conclude that there's nothing in this data to suggest a difference in miles driven as employees went from a 5-day work week to a 4-day work week. What we really want to do here is not to analyze the two sets separately, but rather to take advantage of the pairing and analyze the difference in miles driven. So you will notice a third column has been created that records the difference in miles driven, the 5-day-a-week figure minus the 4-day-a-week figure. Negative values indicate that that employee actually drove more miles annually on the 4-day work week schedule. Now we have a single set of observations to analyze, and if we wanted to, we could use the t-statistic formula from Chapter 8 on this column of differences and perform the test of significance. So when we analyze pairs data, we really analyze the difference between the pairs, not the original data. It is important to note the general form of the null hypothesis. It says that the mean difference is 0. The subscript D stands for difference. Rather than perform the t-test by hand, we will load the data or type the data into StatCrunch. From the Stat menu, we choose the paired t-test and then specify that the data is in columns labeled 5-day mileage and 4-day mileage. Notice I have checked off the box that says Save Differences. Next, we choose Hypothesis Test and specify that the hypothesized difference is 0 and that we have a two-sided alternative. Our program reports a test statistic of 2.89 and a p-value of 0.0167. It also tells us that it has created a new column of data called Difference that contains paired differences. Next, we re-perform the test and this time select confidence interval, a 95% confidence interval, and the limits of the confidence interval are displayed in the table. They're from 221 miles to 1,755 miles. This slide puts it all together. There is the statement of both the null and alternative hypothesis, the value of both the t-statistic and the p-value, a decision to reject the null hypothesis since the p-value was less than 0.05, and a clear statement of what this means, namely that on average employees drive fewer miles annually on the 4-day workweek schedule than the 5-day workweek schedule. Every time we reject a null hypothesis, we must mention the p-value. Here the p-value of 0.02 assures everyone reading our decision that the probability we have reached the wrong conclusion is at most 2%. StatCrunch was used to get the 95% confidence interval, which can be interpreted as, we are 95% confident that on average employees will drive between 221 miles and 1,754 miles less annually on the 4-day workweek schedule than the 5-day workweek schedule. Next, we address the question of how the ages of husbands and wives compare. It is generally thought that husbands tend to be older than their wives. As society changes, is this still true? Let's see what we can conclude using data from 16 randomly chosen married couples. First, notice the pairing. The basis for matching data here is not that observations are taken on the same person, but rather the matching criterion is husband and wife. We are clearly interested in the difference in age of a husband and his wife. Notice that the difference I computed were husband's age minus wife's age. I did this since for most couples the husband's age was larger than the wife's age, and positive differences are easier to interpret. Here I am presenting the results that I got by loading this data into StatCrunch and running a paired t-test followed by a 95% confidence interval. Since the question asked if there is evidence that husbands tend to be older than their wives, I decided to use a one-sided test, and I made sure I specified this when I ran StatCrunch. Now our p-value is slightly above 0.05, so we failed to reject the null hypothesis. As a result, we must conclude that there is not any evidence in this data that would suggest that husbands are on average older than their wives. The null hypothesis of no difference in age could be correct. Notice how the 95% interval includes 0. Once again, an indication that the difference in age could in fact be 0. In cases like this, when the confidence interval includes 0, it is not important to try to interpret the boundary values. You only need to mention that since 0 is included in the interval, it means there could be no difference in the average ages.